Hello. So today what I want us to go over is derivatives of more functions, um, specifically functions that we cannot rewrite so that it looks something like this, right? We already know how to deal with those. So anything that can be rewritten as x to some power, that covers all sorts of polynomials, quadratics, cubics, and more. It includes radicals, right? Because we can just rewrite it as a rational exponent. And it also includes things like rational functions, because we know that we can just use negative exponents. So there's quite a bit of functions we know how to deal with just with the power rule. And then on top of it, right, so we know anything that can be rewritten like this. We also have our product rule and quotient rule, and chain rule, which are applicable not just to x to some power, right? We can use it for anything. But we noticed that even more complicated functions we were able to tackle once we knew those rules. And then in addition, we explored e to the x. But there are still at least 3 common functions that we've seen a lot in algebra that we have not discussed here yet. And so what we want to know is how to deal with those. So today we're going to look at a to the x. So other exponential functions where the base is not e, right? The base is some other number that is not e. We want to look at natural log of x, and specifically it's the natural log if you, so I guess I should say log base e, right? This is going to be easy, but if you kind of put these together, you could probably figure out how to find other logs, although those almost never come up in my experience. This is the one we use and see the most, so I'm just going to focus on this guy. But like I said, you could find this, and it is a different derivative, but I'm not going to go over it here in this video. And then the last one is absolute value of x. So I think we can all agree that we've seen this quite a bit in our algebra days, right? Pre-calculus stuff. And we have not yet talked about how to find the derivatives of them. So that's what we want to tackle now. So let's go ahead and start with a to the x. So we had y equals a to the x. So I'm going to go ahead and let you pause and think about this for a second. And then after you've thought about it, go ahead and join us. Okay, so if you look at this thing, obviously we have not talked about it yet. So you're probably like, yeah, I don't know what y prime should be. What is dy dx? We don't know. But it does look similar to a derivative we do know, which is e to the x, because they're both exponential functions. So maybe a good place to start, since we know, like, if y equals e to the x, then dy dx is e to the x, right? Like, we know this. Is it possible to rewrite this exponential that has base a using e to the x somewhere in it? Because if we did have that, now it's something maybe more approachable. So let's think about that now. Go ahead and pause. I want you to think, how can we rewrite a to the x so that it looks like e to the something? What could we put in this box? So the way that we're going to tackle this is by recalling some properties between exponential functions and logarithmic functions. We know that logs and exponentials are inverse functions, and we know that inverse functions undo each other. Meaning if I have natural log of e to the, I don't know, stuff, because these are the same base, right? This is base e, this is base e, and the fact that they are inverses, these actually undo each other, and the m gets to break free, right? The m just is there by itself. And so that means if you started with an m and you put like, gave it a base e, and then right after you took the natural log of it, it's almost like you didn't do anything at all, because these guys just undo each other. It's the same thing as if you had m plus 3 and then minus 3, right? You changed it, but then you undid that change. And so that's what we're going to want to do here, is figure out how could we play with e and natural log so that I'm changing it, but I'm not really changing it. I want it to still be a to the x. And so if you, maybe you could pause here if you want, but if we see this, right, this is kind of the opposite version where the natural log's on the outside. We can also do e to the natural log of n. Those also undo each other in the same way. So here I can do e to the natural log, and the thing that I want inside is whatever's over here, the thing I'm playing with. So I want this to be a to the x, okay? So now we have rewritten a to the x we know is equal to e to the natural log of a to the x. Cool, looks messy, right? This is gonna be nicer. So at this point, I'm looking at this and I'm saying, okay, I know that I wanna deal with e to the x, e to the x. I also know how to deal with e to the 2x or e to some number x, right? Because we have chain rule. So my goal is I need this x that's in here to not be up there. I want it to be maybe right here. And the question is, have I set it up so that I can actually bring it down? And the answer is yes, because if we think about our properties of logs, we know that log of x to some power is the same thing as if we bring this power down, right? Because logs and exponentials are inverses, so logs, they do undo exponents no matter what, in the sense that the exponent doesn't stay up in the exponent. They can come on to the ground where we can play with them. And so the fact that we have a log here means that this exponent can come down in front like that. And so if we rewrite it, we have a to the x is the same thing as e to the x natural log of a. And this is precisely what I need, because if you think about it, a, although it doesn't look like a number, if it's an exponential function, a is the base, which means it is some constant number. It's not a variable, it's not changing. it's a placeholder for a number, but once we put that number in, it's never going to vary, right? That number is going to remain the same value, and therefore natural log of a constant, this is just a number. So now we have the situation e to the x, right? E to some number times x, and we know how to deal with that with chain rule. And so we're all set up to go here. And so we can go ahead and try and find the derivative. So we know the derivative of a to the x is going to be the derivative of e to the x natural log of a and by chain rule, we know derivative of e to the stuff, right, is just going to be e to that stuff. But then by chain rule times the derivative of this inside portion right here. And if we take the derivative of that, so natural log of a. If we just look at that and spruce it back up a bit, because derivative of a to the x, we get equals e to the x natural log of a times natural log of a. But this is silly because really this was just our way of rewriting a to the x, right? E to the x natural log of a. If I bring that back up, then I have e to the natural log of a to the x, and these undo each other, so this really is just a to the x. That's what I started with. And so this is just a to the x times natural log. That is the derivative of these exponential functions. So now, if I said y equals 2 to the x, you can find dy dx. Go ahead and try it right now. All right, so I'm assuming you hit pause. Make sure you did it. So the derivative of 2 to the x, we see is just going to have a copy, just like e to the x. But because it's not e, we're going to times by the natural log of whatever that base was. Yay! And we're done. All right, the next one that I want to look at is y equals natural log of x. Okay, now this is similar to the last one where we might think, all right, we don't know how to do this, but we know natural log is base e. And we do know e to the x, so maybe we could try to rewrite this so it looks more like e to the something. Okay. And in this case, we're going to do it in a slightly different way, but I would argue it's a much nicer way because there's a little less stuff going on. So go ahead and pause and think about this. How could we rewrite this thing so that it's e to the something? All right, so if we look at this, do you notice that if I have y equals natural log of x, I can use my undo property, give it a base e, that'll undo this, and what I do to one side, I do to the other. So e to the y is equal to x. Now it looks like e to the something. And at this point, if we got e to the something, we're going to go ahead and try and take the derivative. So d dx. So the derivative of e to the something is going to be e to the something. But if you notice, this variable in the exponent is different than the variable we are taking the derivative with respect to. That's precisely what chain rule is, right? We can take care of it using chain rule. And the way we do that is just by multiplying by the derivative of y. Well, the derivative of y with respect to x is just dy dx, right? We smush it. Different variables, like nothing. Leibniz notation is just like, just put them together. Like I can't really do much with it, right? Equals derivative of x with respect to x. Well, those are the same variable, and therefore we can take the derivative, it's just 1. So if you look at what we started with, we have y equals natural log of x, and we were trying to find dy dx, right? Let's check back in here. Right? I mean, this is where we're at. It was more like a let's check back in with what was our goal, right? Do you see perhaps a way we can find dy dx? That's exactly what we got right here. And so if I'm trying to get dy dx alone, right, if I'm trying to solve for it, what would we have to do here? Divide by e to the y. Okay. Get dy dx all by itself. And so now we're going to have, I ran out of room, so let's move it right here. Dy dx equals 1 over e to the y. And it's like, cool. I mean, that's it. But again, let's think back to what we tried to rewrite this so it was e to the y, right? But originally we had a function of x's. So do we know what e to the y is in terms of x? Our goal is let's go back to x. And thankfully, if you look right here, right, e to the y is actually just equal to x. And so dy dx is equal to 1 over x. This is the derivative of the natural log. D dx of natural log of x is 1 over x. And so let's try one. Let's do all right, so the derivative of 3 times natural log of x, well, the 3 is just going to stick around here 3 times. This is the thing we have to take the derivative of. And the derivative of natural log of x is 1 over x. So this is just 3. Now let's try y equals negative natural log of x squared plus 1. So go ahead and pause and try this one. All right, so the derivative, we got this negative, so negative times whatever the derivative of natural log of all this. Well, anytime you have the natural log of stuff, right? Before we were just saying all that stuff was x. But if the stuff gets more interesting, like we have here, it's okay. The derivative will still always be 1 over copy and paste this stuff. So I'm just going to copy and paste x squared plus 1. And then by chain rule, I'm going to multiply, let's do a different color actually, right? We're going to multiply by the derivative of the inside. And this is where we get to actually take the derivative of the more interesting stuff that we put in there. And so chain rule, tag on a chain, derivative of x squared plus 1 is 2x, and thus our final answer will be negative 2x over x squared plus 1. So the last one we're going to look at is absolute value of x. What we've seen in this class already is the absolute value of x, like first of all, is going to bring up a graph because we've seen absolute values come up with limits, right? And so we saw that just kind of having a visual of what was going on was sometimes helpful. And so if we're trying to find the derivative of this, remember the derivative is the slope of the tangent line. If you think of the slope of the tangent line here, over on this half, because there's kind of two halves of this graph, right? There's this negative sloping one, and there's also this positive sloping one. Slope of the tangent line here, could probably figure that out. Slope of the tangent line here, we could probably figure it out. But we would have to kind of pull this graph apart and think of it separately. And so, like I was alluding to, is we've definitely seen how to rewrite an absolute value so it's in those two separate pieces. It is. If we're positive, right, we stay the same. And if we're negative, we negate, right, give it an extra negative so it kind of bumps us back to positive. And then on one of those, we say, 0 works in either case, so we usually put it there, whatever. The second you see these two individual pieces, right, as soon as we drop the absolute value bars, I hope you realize that we know how to take the derivative of this, right? The derivative of x, so if we have y prime, derivative of x is just 1, and the derivative of negative x is negative 1. And that looks about right, because slope of a tangent line, we can see it's a negative slope, right? So it's telling us the slope is negative 1. And over here, on the positive side, it's telling us the slope is 1. What about here, though? What about right at this point, where the two halves meet, right at x equals 0? What's going on there? Because I would say I can't tell if that's a part of this side, or if it's a part of this side, or if it's doing its own thing. Like, what's going on here, right? How would we draw the tangent line at this point that's so sharp? And you might remember that because of that sharp transition, right, the slopes of the tangent lines change from a negative one to a positive one so quickly in an instant that right at x equals 0, the derivative does not exist, because it's impossible to state what the slope of the tangent line is right at x equals 0. So we say, maybe let's put a note, y prime does not exist at x equals 0. The word to describe this shape is it's a corner. You can maybe call it a cusp, right? But sharp points on a graph are where the function is not differentiable. And so on our derivative function over here, we can just say x is greater than 0 only, right? Or x is less than 0 only. And we can see that the original function was including 0, but when we look at the derivative, 0 is no longer included because of the fact it's a corner. All right. So now we've tackled the derivatives of these 3 other basic functions we've seen in algebra, and we know how to take the derivative of pretty much any function. So thanks for watching, and I'll see you next time.